And the first kind of problem we're going to do is the mole-to-mole stoichiometry problems. This is a review because we've already tackled this in the previous lesson. However, we're reviewing it because in any type of stoichiometry problem, you always have to do at least one mole-to-mole conversion. Remember that the mole is always the bridge between any type of grams or counting number that we use in chemistry, whether that be atoms or molecules. And that's the case for stoichiometry in conversions with chemical reactions as well. So it's going to be the case for all of these types of problems. So the chemical reaction we're going to use is going to be the same chemical reaction for all of our problems, just to keep it simple. Copper 2 oxide, which is a mineral form of copper, it can be mined, and it's actually one of the most common minerals that is mined for copper. We can convert it into pure copper if we follow the following process. We react it with pure carbon as a solid under high heat, and we can produce the pure form of copper along with carbon dioxide gas. So our scenario is that if we have 4.05 moles of copper oxide, and we need to convert that to pure copper, how many moles of pure carbon do we need, and how many moles of carbon dioxide gas will we make? Well, we know that we're starting off with moles of one substance, that being our moles of copper oxide, and we're converting straight to moles of another substance. We'll tackle the carbon first, but what should we always do before we do any type of stoichiometry is make sure our reaction is balanced, our equation is balanced. We notice here that we have two oxygens. And over here we only have, on the reactant side, we have one, so we'll put a 2 in front of our copper 2 oxide. That balances out our oxygens. Now we have two coppers that we have to contend with, so that will balance our coppers, and we have a balanced reaction. Now that our reaction is balanced, we can proceed with the problem. So we need to convert copper oxide moles into moles of carbon. And so that means we're going to use the ratio between copper oxide and carbon, which is a 2-to-1 ratio. Therefore, moles of copper oxide must go on the bottom so they cancel out, and then we're converting to carbon, so moles of carbon will go on top. Our ratio again was 2 moles of copper oxide to 1 mole of carbon. These units will cancel. Therefore, we are dividing by 2 in our first problem. And so our math is going to be 4.05 divided by 2 to 3 sig figs. And I get 2.025. And since we're rounding to 3 sig figs, 2, we look to the 5. Oh, there's nothing after the 5. We get that funny 5 rounding rule. We want to keep it even. So this will actually end up being 2.02 moles of carbon. So that's the answer to the first problem. The second problem wants to know how many moles of carbon dioxide. So we still start with the same amount, 4.05 moles of copper oxide. Our ratio will just be different because now instead of comparing carbon, we're comparing it to copper oxide or carbon dioxide. Well, it's actually the same ratio because they have the same coefficient. So we're still going to use a 1 to 2. It's just our unit is different. It's now carbon dioxide, which means that it will be the same answer, right? Because we're doing the same exact math, right? That's convenient. 2.02. I don't know why I'm doing that. It's because I'm looking at the one above. 2.02 moles of carbon dioxide as well. So we're going to produce 2.02 moles of both carbon and carbon dioxide.